Hi, I'm going to do a two-part series of videos on refraction, or Snell's Law. So refraction is the bending of light, and we have some interesting rules that we have about the bending of light, but it's pretty easy actually. I like Snell's Law because it's simple, very symmetric, and once you keep track of your angle, it's all good. So refraction is the bending of light when it changes media, from one medium to another medium, from one material to another. And the bending of light is determined, how much that light bends when it changes media is determined by two things. It's determined by the angle that the light's coming in at, and it's determined by what materials it's moving through. So going from one material to another material. So an example is if we've got air and we've got water. Suppose we have a light ray coming in from air and then it moves into the water. What happens when it moves into the water is that it comes off at a different angle than it was traveling at in the air. And with Snell's Law, the thing that most people struggle with the most is this idea of the normal. So the normal is the perpendicular to the surface, and all of our angles when we talk about refraction are measured to this normal. So don't ever do this one. We want the angle from the normal. So this is our angle of air. This is the angle of water. And just kind of rule of thumb is when we go from, oops, backwards. Do it this way. When we go from a material that is less dense to more dense, so optically dense. It's an analogy, but it's a pretty good analogy. So air, it's easy to travel through, so that's a low density material. Water is a little harder for light to travel through, so it's a little higher density. When this happens, less dense to more dense, then the light bends towards the normal. So it bends towards the normal. Uh-oh. As we have here. So it would normally come in here, and as soon as it hits the water, it bends whoop, towards the normal. So we can have the opposite as well. If we have something going from a more dense to a less dense, so if we go from water to air, so more dense to less, then you can probably guess the light is going to bend away from the normal. Away from the normal. So here, if we have something, a light ray in water, coming up from the water and trying to leave into the air, what it's going to do is it would normally, if there was no transition, no air there, it would keep going here, but we're going into something less dense, which means we bend away from the normal. So it's going to come out something like that. But we still measure the angles from the normal. So here's our new angle in water, here's our new angle in air. So we can go either way, doesn't matter. And when we go into a more dense material, the light bends towards the normal. When we go into a less dense material, the light bends away from the normal. So these are two good things to keep in mind just as a way to check your answer, I guess is the best way to do it. So check your answer. Now, I said that there are two things that affect the amount of bending, the material and the angle. The material, we measure the optical density, if you call it, by something called the index of refraction. And index means number, so this is purely a number. There's no units associated with it. It is a ratio of the of the speed of light in a material as compared to the speed of light in a vacuum. So if air is pretty close to a vacuum, well, the index of refraction of air is 1.00. In water, which is a little more dense, the index of refraction of water is 1.33. And these are on your equation sheet, but you'll probably remember them because you're going to see them so often. So the index of refraction, just a number telling you how easy or hard it is for an object, for light to travel in that material. The numbers we're going to see, the lowest we'll ever see is 1. And the biggest we typically will deal with is up around 2.5, somewhere around there. So the index of refraction is telling us about the material, the optical density of the material, and then the amount of bending also depends on the angle. So whatever angle it's coming in at. And those two variables lead us to Snell's Law, which is this great symmetric thing, Snell's Law. So N1 sine theta 1 equals N2 sine theta 2, where this is for the first material, this is for the second material. Index of refraction of the first material times the sine of the angle from the normal in the first material equals index of refraction of the second material, water, times the sine of the angle in water. So for air to water, that's what it would look like. So nice and symmetric, easy to deal with. So that is Snell's Law. Let's do a real quick problem going from a little bit different angle. All right, I'm going to erase this bit. So I'm going to give you a problem on fiber optics, because fiber optics are just fun. And, you know, we hear about them. We hear that's how we get fast internet is through fiber optics, but how is light behaving in a fiber optic system? All right, I'm going to leave the equation up, but we'll erase the rest of it. Okay, so our problem. Let's make sure. Okay, still recording. Light travels from air into an optical fiber, a fiber optic cable, with an index of refraction of 1.44. There are three questions. The first question, in which direction does the light bend? Second question, if the angle of incidence on the end of the fiber is 22 degrees, what is the angle of refraction inside the fiber? And the third question, sketch the path of light as it changes media. All right, so we have a fiber optic cable, so just a long cable. And we're going to have light hitting the end of the cable and going from the air into the cable. Now, this is the surface it's going to hit. So if the surface it's going to hit is like this, the normal is perpendicular. So my normal line is going to be drawn like that. Okay, and we're going to have light coming in to the end of the fiber from air, which has an index of refraction of 1.00, into the fiber optics, which has an index of refraction of 1.44. So, good problem-solving strategy. Start with a picture. All right, so which way is light going to bend is the first question. Well, we're going from 1.0 to 1.44. We're going into something that's more optically dense. So from less to more dense means that the light should bend towards the normal. I would expect, instead of continuing on in the fiber optic like that, it would go whoop, bend towards the normal. So something, oh boy, it's not very clear, is it? Let's make this a steeper angle coming in. So if it comes in like that, it's going to bend that way. That's my guess. All right, so if it's coming in to the end of the fiber at 22 degrees, what is the angle of refraction inside the fiber? All right, we're told this is 22 degrees. And again, from the normal. Okay, so how do we do this? Well, when I'm doing a refraction problem, one of the first things I will do is figure out what materials I'm going from and to. So what media to what media. In this case, I'm going from air into fiber optics. That means that this equation, if I rewrite my Snell's Law equation, is going to be index of refraction of air times the sine of the angle in air equals index of refraction of the fiber optic times the sine of the angle fiber optic. Okay, now what do I know? Well, I know that. I know that. I know both indices of refraction, and I'm given that the angle in air is 22, and I want to know this. Got it? I can solve this. It's already there. 1.0 times the sine of 22 equals 1.44, oh, squeaky marker, sine of the angle in the fiber optic. And so I want to solve for this. That's the only unknown. We got this. This 1.0, I'm just going to ignore it because it doesn't change anything. Nice when we have air. So, okay, if I get rid of the sine 22, then I'm going to bring the 1.44 over to the other side. So divide both sides by 1.44. That'll give me this equals the sine of the angle in the fiber optic. And now I want to get rid of the sine. So you can't just divide by the sine because the sine alone doesn't mean anything. This whole thing is one chunk. So you can't divide by the sine because that doesn't, it's got no meaning. The sine always has to be associated with an angle. So how do we get rid of a sine? Well, that's where the inverse sine comes in. If I do the inverse sine of both sides, so the inverse sine of this piece, sine of 22 degrees over 1.44, and then I do the inverse sine of the right-hand side, sine of the angle in fiber optics. Okay, well, this and this cancel each other out. It's the same as doing the square root of x squared. Well, that's x. This and this cancel each other out. The inverse sine and the sine cancel each other out. So on the right-hand side, gone, gone, I'm just left with the angle. So to calculate the angle in the fiber optic, I'm going to do the inverse sine of the sine of 22 divided by 1.44. And when I make that calculation, I get 15 degrees. So does that make sense? Well, I thought that it would bend towards the normal. And so now this angle here, oh boy, is 15 degrees. So that is less than a 22, yep, which makes sense. The third question was sketch the path of light. Well, I just did that. So the light comes in at 22, it bends towards the normal to come through the fiber optic cable at 15 degrees from the normal. So that's just a basic refraction question. The only real hard part about Snell's law and refraction is remembering that the angle is to the normal. So if I ever give you an angle to a surface, I'm seeing if you're awake or just or if you're paying attention, I guess. So always, always, always angle is from the normal. All right, I think that's a good start. The next video is going to be going the other way from fiber optic into air, and we'll see what happens there. All right, good job.